Welcome everyone. Nice to see you and to begin this new season of the Circular Industries Talks. Ruud is gonna launch this new season with his presentation, and Ruud is also the new chair of the Circular Industries team at Leiden-Delft-Erasmus Center for Sustainability. So he's replacing René Klein. So Ruud, you are Professor Circular Product Design, and your research focuses on how to design products to enable lifetime extensions through our strategies like reuse, repair, manufacturing, recycling. And actually, which is very nice about industrial design engineering, the faculty you're at TU Delft, is that you are really at the interface between technology, business, and also user behavior. So to see how all function together to enable circular economy. So that's very nice. And floor is yours. So for the people newly joining you, usually we do the presentation. You can or ask question via the chat during the presentation, or keep them for the end. So at the end we have a Q&A session. So it's a bit up to you. The floor is yours.
Okay. Thank you, Elise, and good morning, everyone. It's a pleasure for me to take over the moderation of these circular industry talks from René, and to have today the opportunity to introduce myself, but especially I think my interest in circularity by presenting some of our work on circular product design. You are all aware of the basics of a circular economy. We take materials, make products, use them, then dispose them, and hopefully part of the material is recycled. But the extent to which we do this will largely depend on the design of a product. And more interesting than recovering the materials is to keep products alive. We can resist obsolescence by improving the durability of products. We can postpone obsolescence by enabling maintenance, repair, upgradability. And we can reverse obsolescence through refurbishment, remanufacturing, parts harvesting. The main challenge here is how the design can enable multiple life cycles, also for single-use products like packaging, or for products with extremely long lifetimes like wind turbines. Technology enabling reuse, repair, remanufacturing is one thing, but getting it implemented needs considerable additional effort and confronts us with the full complexity of the system. Implementing often asks for a different way of offering the products, new business approaches. Reverse logistics needs to be set up. Financing also might become an issue if products are kept as assets on the balance. The relations with other companies and users changes, and it brings also changes in responsibility, might raise ethical questions. And our metrics need to change. This means that we need new ways to assess the effectivity regarding economic, social, and from our perspective, especially environmental goals. We don't do all those things in our group, of course. In our group, we have a focus on design, specifically design for the circular economy. And this leads to a diversity of activities. Which focus on recovery pathways, with currently especially emphasis on repair and recycling. We focus on specific product categories, with some emphasis on electronics and medical systems, and on a number of material systems like composites and bio-based materials. In this talk today, I do not want to talk briefly about all these topics. I prefer to focus on just two of them to dive a bit deeper and to illustrate something of our approach and show you some actual results and discuss opportunities and dilemmas of circular product design. Repair is an example where we in the meantime have acquired insights that really help us to guide and assess design. Bio-based materials, on the other hand, is a topic where we are still early on the learning curve. Not even close to definite answers, but a very important topic to get right, and therefore I think also interesting to discuss here. So the first topic I want to discuss is repair. And this slide shows what we are up against. In most cases, repair of a broken product is not even considered. And if repair is carried out, the odds that it is successful are smaller than the odds that repair fails. And this is related to the ease of repair, which is not exclusively the domain of design, but where design has a very large influence. And as I said, often repair is not even considered. This Norwegian survey provides some insight in why people choose to replace instead of repair a product. And then you see that there's expectations about lifetime, which generally is quite short, and quite some economic arguments are dominant. Often it's also made very hard to repair a product yourself and unaffordable to let it repair. But there is a counter movement. And for the consumer electronics industry, it becomes increasingly relevant due to all kinds of user actions like the right of repair movement. In the meantime, this has resulted, at least in Europe, in regulations, and in France also in more specific legislation. This is, for instance, reflected by repairability scoring systems. We investigated a number of them as part of a European project, the PROMPT project, on preventing premature obsolescence. And mostly when we think about ease of repairability, we think about the ease of assembly, taking apart a product, the tools that you need for that purpose. But there's a number of other factors that are also important. For instance, diagnosis, which is hardly addressed by any of the scoring systems. Also, software-related factors are of growing importance. An example is devices, Apple iPhones, for instance, where you need software pairing of spare parts to your phone, and otherwise, even if the part is an original part, it won't work. And of course, also just failure caused by software or failure caused by the lack of software upgrades. And of course, repair also is not just about technical feasibility, also the affordability of repair is of crucial importance. To get some more insight in these things, we looked into a number of different scoring systems and we evaluated a number of products to see how they scored, but we were not really interested in the scores themselves, but in how the scoring systems evaluated the products. And for that purpose, we also thought of two completely hypothetical products. One which could not be disassembled, and one that has prohibitively expensive spare parts. And as you can see here at the right, these products get extremely high scores, and that's related to the fact that the scores are determined by subscores on different types of topics. Ease of disassembly, information accessibility, spare part availability, spare price availability, spare part price, and software aspects. And if you have a low score on, for instance, ease of disassembly of one of the priority components, you can still have a reasonable score for disassembly at large, and all the other scores can be optimal, so you can reach a very high value. This is something that can be easily tackled by not simply adding all the subscores, but by introducing, for instance, threshold scores, and that's one of the results that, as a conclusion of that European project we have proposed. Anyhow, scoring systems highlight the importance of ease of repair, but how to make it easy for a product to be repaired. And therefore, I would like to look into the example of a vacuum cleaner and see how the product architecture affects the repairability and how design is able to assess the bottlenecks and indicate improvements. The work that I will show you in the upcoming slides was done by a former graduation student, Francesco De Fazio, who in the meantime is working for Accenture van Berlo. So the first step in assessing the ease of disassembly is something that we do by making a disassembly map. This basically is a layout of the product architecture. It represents, depicts how the components are connected to each other. So all these light blue circles are components, and the importance of this disassembly map is not in the components, but it is in the connections, which are indicated by various shapes and colors. The shapes indicate the type of tool that is used, and the colors indicate the level of difficulty, for instance, the force or other difficulties that you might encounter that might make it time consuming to dismantle a particular part. What you further see is some indicators that say something about the relevance of a particular part. And we now just have a look at the top of this disassembly map. You can see that the map goes down quite long, and this is an overview of the total map, but hardly readable. But as you can see, a number of parts is hidden quite deeply inside the device. And at this point, I would like to make a small sidestep, because many of the scoring systems that I just mentioned use step depth as a measure of the ease of disassembly. So you just count the number of steps that you need to reach a particular component, and that determines the ease of disassembly. But this neglects, of course, the difficulty that some connections might pose. It's therefore a fairly inaccurate way of assessing the ease of disassembly. More informative would it be to use the time needed, but of course that shows quite some variation. And what we did again in the already mentioned PROM project is establishing so-called proxy times. In this project, a large number of TVs, vacuum cleaners, smartphones and washing machines was disassembled by professional testing labs, and we recorded all disassembly and reassembly actions and determined the time needed for specific connectors. The result is shown in this graph, which allows us to use particular average timings for groups. So in the case of particular tools, and this, by the way, is a plot that shows manipulation steps. So positioning tools, putting them away. All these bars that you see indicates separate measurements, the timing of separate measurements. So you see that there's quite some distribution, but nevertheless, it allows to group particular actions and to determine average timings. And with those average timings, we subsequently analyze the disassembly times of a number of products. And then here in this graph, you see in the greenish, bluish circles, squares and triangles, products assessed by the proxy time, and the red indicators are the same products but assessed by the step method. And then you see that, on the horizontal axis, you can see the actual time. The vertical axis depicts the time based on the proxy timings and purely the disassembly map. And what you then see is that the method based on proxy times indeed gives a far better estimate. It's a far more accurate estimate with less spread in the total time needed than the timing based on the step method. So this is a way, based on an analysis of the product architecture, this assembly map, combined with proxy times to directly calculate the likely disassembly time. And this will be a step forward in assessing, but also in providing guidance to designers to design in a way that makes a product as easy as possible to disassemble. So that was a side step. Let's get back to our vacuum cleaner. We have seen the disassembly map. We have seen something about potential timings. Here you see the constituting parts of this vacuum cleaner, but not all parts are equal. We need to pay special attention to parts that have a high failure rate, are critical to deliver the function of the products, or might otherwise be of special concern. And those are the priority parts, which are here indicated with the red circles. Where do we find these in the product? Well, some of them, as you can see, at the top, but also quite a lot at the very bottom. These are anyhow laborious to reach, even if all connections would be easy ones, which is not the case. So, how to deal with this from a design perspective? Fortunately, Francesco liked pancakes, but as an Italian, he is also quite critical on which one he wants to take. And what do you do when you want one that is at the bottom of the stack? Indeed, you clump. You just take the entire stack and you don't put them one by one at another stack. So, could you do something similar with priority components at the bottom of a stack? And of course, the answer is yes, otherwise I wouldn't have shown you this. Taking the disassembly map as a starting point, you might consider which parts can be clumped into a single module, and in this way you can largely decrease the disassembly map depth to the deeper incorporated parts. And when you clump these as a single module, your disassembly map subsequently looks like this. And what he basically did is all these parts are now grouped in a single module. And of course, the module itself can be also disassembled if needed, but the parts below this module are far easier to reach. And that is shown by these two movies. I hope that also online this will be clear. The current design is on the left, the redesign on the right. And you see that the redesign already is done. And I will skip the remainder of the movie because the current design will take another 2 minutes to get at the same level of depth. And this was achieved, by the way, by just shifting the position of 2 screws. In this case, it's really a very easy effort in the end. In many cases, of course, it will require a somewhat larger redesign, but it shows the effectivity of the approach and also the guidance that you can obtain by closely studying such a disassembly map. Well, summarizing the repair part, repair is something where over the past years we have gained a lot of insight, where we have developed clear guidelines for design for repair, and where we are now able to assess repairability based on product architecture without the need of testing. Directions in which we are now further developing our repair insights focus on spare part manufacturing through additive manufacturing, 3D printing, and also on consumer behavior in those approaches to stimulate repair. And further, we are quite interested now also in the tensions between design for recycling and design for repair. What can we do to make sure that both circular strategies can be fulfilled? Now I want to shift to a completely different topic, from a product focus to a material focus. And I've chosen for a focus on bio-based materials because but we are also working on composite materials and electronic materials, the latter especially with respect to recycling. But bio-based materials pose a number of special challenges, I would say. In the butterfly diagram, bio-based materials have their own biocycle that focuses on regenerative materials, contrasting them to materials that cannot be replenished. And those materials are in the technocycle. And whereas in the technocycle, recycling is always a necessity, in the biocycle, materials can be decomposed completely, preferably in a cascade of steps. But basically, you rebuild based on a natural cycle. And for the following, I will really focus on bio-based plastics and not include all kinds of natural materials. And we basically distinguish two categories here. The first one is plastics that are based on unique bio-based building blocks, of which PLA is the best known example. And the second is drop-in polymers. And these polymers are basically identical to existing petrochemical polymers. The best known examples of bio are bio-PE and bio-PET. From a design perspective, these are not very challenging, as basically product design doesn't need to change. Although we do get additional recovery pathways where we might need to take into account something for how to treat the product at end of life. Bio-based plastics are often considered biodegradable. But the last two examples that I mentioned, bio-PE, bio-PET, already show that this is not the case. And this is a very important thing to stress. Bio-based relates to the source of the plastic, while biodegradable gives information over a possible end-of-life pathway. And only a limited number of bio-based plastics is also biodegradable and often only under industrial conditions, while there's also petrochemical plastics that are biodegradable. So I would now like to take a life cycle perspective on bio-based plastics. And then the first thing to look into is sourcing of the material. That is the crops that are used. The nature of the crop, is the crop competing with food, the land use that is needed, water use of fertilizers, pesticides, all these factors cause impacts. The benefit, as we will see, is in the carbon dioxide that is taken from the atmosphere. But here we have also a number of impacts that might be potentially negative. And that's shown in this figure, maybe a bit of a complicated one. The figure shows ACPE. In particular, drop-in bio-based plastics. And it shows that the impact is very dependent on the sourcing and shows far more variation than the petrochemical plastics that you see here at the end. The final value is indicated by the dots, and the color bars indicate the effects of crop cultivation and of various subsequent chemical processes that are carried out to fabricate a polymer. And the negative part that you see is due to the sequestering of carbon from the air in the bio-based polymers. The impact is related to the nature of the crop, as said, but also strongly related to the location. So here you see wheat in two different locations, and in one case the net value is negative, in the other case the net value is positive and even far larger than that of the bio-based materials, the petrochemical plastics. And this is especially related to the energy mixtures that are used during all kinds of processing. Note also that the values are sometimes negative, so the net value is negative. That is because carbon is stored in the plastic. But also upon incineration, this carbon is returned as carbon dioxide to the atmosphere, and in that case the negative effect is again lost. Then it becomes more climate neutral. But also in the case of the petrochemical plastics, the CO2 on incineration, CO2 is emitted to the atmosphere on incineration. So the difference that you see remains the same also after incineration. This graph basically shows that there is a huge and important advantage of bio-based plastics potentially if you do sourcing and the choice of the nature of the crop correctly. If you don't care, you might be even worse off than with petrochemical plastics. And then, of course, there are some additional impacts. And in those cases, you often see that, bio-based plastics need more water, fertilizer, pesticides that have impact on toxicity. And in categories related to these things, you will see that petrochemical plastics in general perform slightly better, but overall the potential gains of bio-based plastics on global warming potential really dominate all other impact factors. Continuing with the life cycle, once the crop is harvested and processing is needed, that is different from the petrochemical processing. Will have different impacts. I showed part of that in the previous slide. But we also turn the polymer into plastic, which usually requires additives. And here questions are these additives also bio-based? And how will they affect end of life? Additives is a thing that is quite often neglected when discussing bio-based materials. The other area in which bio-based plastics are supposed to outperform petrochemical plastics is end of life. And considering all recovery pathways, I would like to first to make clear that bio-based plastics used in products always benefit, or it's always beneficial to keep the product alive as long as possible, just as with all other products. So circular strategies like maintenance repair. Also for recycling, we have largely the same opportunities as for petrochemical plastics. And it's also usually advantageous to have recycling over, say, incineration or composting in the case of biodegradable materials to single molecules, because then you have to rebuild far more to get the materials and the products back. But we do get this one additional opportunity of incineration, and it's an important one. This is not the case for the petrochemical plastics, because here you just return the carbon dioxide that you took out of the atmosphere to the atmosphere, and you don't really add carbon dioxide. And this might be through incineration with energy recovery. It might also be through composting, but realize that in the case of composting, there is no fertilizing effect because it is a polymer that just decomposes completely and doesn't leave any fibers. There's also an important pitfall to note, which is potentially an anaerobic degradation, which is this cycle. It means that you have that your processes take place in the absence of sufficient oxygen, and that might be beneficial when you do it under industrial conditions and make biofuel, for instance. But when this takes place in the atmosphere, you run the risk of adding methane, which has a far higher global warming potential than carbon dioxide. So what should be avoided is uncontrolled biodegradation, as this runs the risk of being more detrimental than burning ordinary plastics. So throwing a biodegradable product as fertilizer on soil, as sometimes is claimed as beneficial in, for instance, cradle to cradle, is nonsense and should be avoided at all costs. In my opinion, biodegradation is mainly useful to avoid microplastic formation in products that inevitably are wearing down. Think of textiles, tires, shoe soles, but don't use it, for instance, in packaging or agricultural films as an excuse to not properly take care of disposal, because then, with respect to microplastics, you create another problem. So far about some of the properties of bio-based plastics. How are they used in practice? Many drop-in plastics can be made, and there's also a large variety of unique bio-based plastics, really ranging from commodity plastics to high-end engineering ones. So basically, you should be able to use them everywhere. But when we look into the type of products in which they are actually used, it's mainly fairly low-end products, predominantly packaging. This is an interesting example of IKEA, who put PLA cups on the market. Great idea, but don't put hot drinks in them, as the glass transition temperature of PLA is rather low and the cup deforms. But we do need this kind of failure and continue experimenting if we want to get on a learning curve where we can replace fossil based plastics by bio-based ones. We carried out a design review of 60 products that are claimed to be bio-based, and the results, to be honest, were disappointing. Similar shape as traditional products, similar performance, often a color in a pastel tone instead of a bright one to make a relation to nature. New marketing, but no new approaches that really use bio-based properties, and no attention to the location of the sources when it comes to impact, and no attention to the specifics of the end-of-life processes related to bio-based plastics. Based on the analysis of the products, we interviewed designers of many of them to discover what drives them and which barriers they perceive. And an important one is that the concept of bio-based is still unclear to many of them. The importance of sourcing, and especially the concept of biodegradability, leads to many misconceptions. But there are also a number of more systemic and economic factors, like the underdeveloped infrastructure for dealing with bio-based plastics, and also infrastructure at end of life. And what also doesn't help is that the market is fairly small and partly monopolistic. At the enabling side, we did see sustainability and communication thereof through design, although we have seen that was mainly a matter of color. And unfortunately, what also wasn't mentioned is the specific properties and how to express their performance. Similar hesitations we did see when interviewing companies making these products, so not the designers, but other people within the company. Uncertainty about the sustainability effect, insufficient knowledge about material properties, relatively expensive, let's say for similar plastics, 30 to 35% more expensive. An underdeveloped value chain, and also a lack of trust in regulations. So given the need to get rid of petrochemical plastics, this basically expresses the need for a research agenda on bio-based plastics to tackle the lack of knowledge on properties, biodegradation, and end-of-life recovery. Further, we should far more actively explore the use and performance of new plastics, and here it will be important to show endurance. I would say failure is an option, see the IKEA example, maybe even a necessity, as experimentation is the most rapid way to get on this learning curve. I want to conclude with a slide that doesn't summarize my talk. I think I summarized both parts briefly already, but that highlights aspects that in my view are important at a somewhat higher level of abstraction. At the left side, you see a number of aspects that directly relate to design. Most important, thinking in multiple life cycles, and really thinking about how strategies to resist, postpone, and reverse obsolescence can be applied through design. Really closing loops at material level, simultaneously with those cycling at the product level. That's why we are interested, for instance, in the tension between repairability and recyclability. And also how to design if you consider not to use fossil fuels at all. Implies renewable energy for the manufacturing, for the use of the product, but also bio-based resources, as I just discussed. At the right-hand side, sorry, I have a phone going. At the right side, you see a number of things that link to design, that affect design, that when it comes to product service systems, we might even study, but that also predominantly the area of other fields. Value chain and network, new collaborative structures, new business models. User behavior is something I hardly address, but it actually is an important aspect in design. Where we also, for instance, looking in with a new product on repair, fixophobia, how we can make repair more interesting, attractive to users. New policies are needed, and increasingly we try also to affect policymakers through the things we find. The PROM project is an example of that. And in assessment, we still need to learn how to assess, especially multiple life cycles, and also how to deal with all kinds of trade-offs and rebounds, which are sometimes difficult to consider in advance. So these topics will certainly return in the next sessions of these circular industry talks. And for now, I would like to thank you for your attention, and I'm glad to continue a discussion with you.
Thank you, Ruud. A lot of information. Very interesting presentation. I think we can start the Q&A. Open the floor for questions. Does anybody have a question? You can raise your hand. Or,
shall I stop sharing, or can we expect quite some
depends if someone wants to discuss a specific
I will leave
slide.
them up for some time, and then...
Yeah, we have questions from Peter.
Yes, thank you for your talk, Ruud. We see a lot of opportunities, but sometimes it collides with the interests of companies. For example, repair focuses on reusing products at a high value level. For companies, that's not interesting because that diminishes their opportunities to sell new products. And as disposal is easy and cheap, it's not an interest. It's often said that regulation is necessary, but maybe pricing could also work. Can you explain a bit what you see as enablers to get these strategies running operational, that it becomes also business-wise interesting, not only morally?
Yes, indeed, a very tricky point for many companies. It depends, in the first place, it depends also on the company strategy. How important is sustainability, for instance, in the company strategy? If you take an attitude of everything that can be made an externality, we deal with as an externality, and we just go ahead, sell more, sell faster. Such companies won't adapt these findings. But all our projects basically are in collaboration with companies that are interested to make next steps. And we also in collaboration with other faculties, by the way, look into sustainable business models. When it comes to things like repair and remanufacturing, it also depends on your business model, whether that might be attractive or not. And a company that focuses on durability and ease of repair might in the end have a much better business proposition to consumers, but not to consumers that go for the lowest price, but maybe to consumers that go for the lowest total cost of ownership. But that we have seen is in the business context something that is far more easy to communicate than to individual users. Regulations, in my view, in that respect, and that's also a reason why we as a group increasingly try to affect regulations, is a very important one. If I look back to the past and then the past 50 years, I don't see many sustainability developments that have not been triggered by regulations. Whether it is the emission of all kinds of toxic materials in the 60s and 70s, energy efficiency driven regulations in the 80s and 90s, the eco-design directive that we have to at least set some recycling targets for, especially electronic products. It's always regulations that force companies to make a next step. So in that respect, in our work, we of course aim at understanding, but we also try to do it in such a way that we set up, develop methods that can be used in practice. For that purpose, we collaborate with manufacturers, with design agencies. But what we reach are to some extent the front runners. With the examples that we set, I hope that we can also indeed stimulate regulations that also make that these front runners get in a more equal playing field.
Thank you for your extensive answer. I take the conclusion of that you do important work, especially on providing good methods for future regulation and bring that under the attention of the policymakers.
I would say that that's something that we strive for, but it's not the main purpose of our work, because that's we are experts in design, and we are not experts in legislation regulations, but we are increasingly aware that we should not only reach the technological, the business community, but that we also should reach out to the regulatory community to make clear what we think that is achievable and how that can be achieved.
Yes, that is important. Thank you.
Any other question? Might be interesting to mention that the white paper on repair to follow that question, because this was actually written by also you partly and other researchers from LDE on repair, and that I put it in the chat, the link to the white paper that we published I think 2 years ago, and that it was also meant for rule makers, but I
think that's a nice example. Yes.
And so just to rebound on what you just discussed. I had some questions. If nobody's shooting, I will shoot. I might have missed some information on everything that you mentioned, but I'm curious about the bioplastics, because you mentioned incineration, degradation, and incineration. Of course, it releases the CO2 that the plant has been captured, or the biomaterial, but degradation as well, no? The compost, I mean.
Oh, composting.
Because you didn't mention it for composting, and I was a bit surprised.
Composting, of course, is something that's only possible with biodegradable plastics.
Yes.
And with composting, you need to take care of a few things. It should be done under the right conditions. So many biodegradable bio-based plastics are, if they are biodegradable, industrially biodegradable, not home compostable. So in home compost, probably nothing will happen. They will just stay there, or will very slowly deteriorate. What is especially critical is that if the conditions are not right, if you have insufficient oxygen, you will have methane formation. If you take the most common biodegradable material, all the food waste that we throw away, if that ends up in landfills, those landfills are known to be significant emitters of methane, because under those conditions you don't have sufficient oxygen for complete decomposition. But further, when we talk about compost, it's basically the large part of the material goes to carbon dioxide and water, and what remains is the minerals and the fibers, and those are fertilizers to ground. But if you have PLA, that is a completely processed plastic. It doesn't contain any minerals, it doesn't contain any fibers. So methane just composes completely to CO2 and water and leaves nothing that is beneficial for the soil.
Yeah, but you say industrial conditions and should be optimal, but for now, any biodegradable plastic that we put in the green bin, it also takes more time than regular biomaterial.
It's even indeed they are claimed to, well, there's a standard for industrial biodegradation, but many industrial facilities where industrial composting takes place don't take the time that is in that standard. So if I don't know the regulation by heart, but if you need to decompose 90% in half a year at 53 or 58 degrees C, but they try to have the process done in 3 months, you will have quite some remains.
But do you know what currently happens with those remains? Because indeed,
I would assume that they are incinerated.
Yeah, okay.
And to be honest, as far as I'm concerned, incineration is a better option than composting. Because in both cases you go to carbon dioxide and water, and in the case of incineration, at least with energy recovery, you recover part of the energy that was stored in the material, which probably is lost when you have the composting process.
Okay. Jan, you have a question?
Yeah, yes, I have a question about the collection system, because in the Netherlands we have a system to collect used plastics. But how does it work with bio-based plastic? Do they have to be separated from other plastics mechanically, or are they just combined with the rest and incinerated with all of the plastics? I have no clue about how that works.
Currently there is no dedicated system for bio-based plastics. So if they end up in compost, industrial compost, they might compost. If they end up in plastic waste, then the current sorting processes mainly focus on things like PE, PP, PET, and the remainder is probably incinerated. So also the bio-based plastics will be incinerated. This, by the way, for the bio-based plastic is far worse than for the petrochemical plastics. But if you want to go to dedicated recycling, you should also have far more dedicated reverse logistics. I would say that is something that is challenging for bioplastics, but basically for plastics quite in general, because also plastics like, for instance, the polyamides that you basically can be that can be recycled, often are not recovered in a stream from which they actually are recycled, and there are many more examples. So that's one of the reasons that on one of the slides I had to remark that reverse logistics need to be further developed, and that might be steps in the separation processes where you go to more advanced levels. It might be pre-selection
by the consumer. That's separate.
By the consumer, but then I immediately realized that it is not something that, well, basically you cannot even ask from a consumer to separate whatever plastic from another plastic, because there's plastics. So you need to find smarter things.
Okay, thanks.
Thanks, Jan. It actually is already what we are asking from the consumer, because you already have multi-layer plastics that the consumer should put in the general bin, and just plastic that the consumer should put in the plastic thing. So it's already asked from the consumer. But anyway, that's a side comment. Are there any other question from the audience? If If not, then we'll adjourn the meeting, I would say. Oh, there's one more question from Ellen.
Yeah, thank you. It's very brief. Ruud, I think you said something about repairophobia? Repairophobia?
Fixophobia.
Fixophobia, is this a project or is this
Fixophobia is an NWO kit project that just started last Monday, I think,
Okay.
formally, and which aims to look into consumer behavior related to repair. Project where also and quite explicitly psychology of consumer behavior is addressed in relation to all kinds of other factors, also legal aspects. So it's a fairly small project, I think 3 or 4 PhDs. At the design side, I'm active in the project together with my colleague Ruud Mugge, professor of sustainable sustainable consumer behavior. We will look into how to enable this by technology-related design aspects. But in this case, it's clearly not a technology push, but really technology used within design to serve particular aims as extracted by the more on psychology behavior-focused partners within the project.
Yeah. Is it already online? Is there, do you know, is there a web page?
I'm not entirely sure. There should be something, I think, a short summary of every project that NWO grants can be found, but the project has started too recently to already have a website, I would say.
I was muted. Thank you everyone for joining. And especially a big thank you to you, Ruud, for giving a presentation. And then, there is no more question. Then we'll see you hopefully over 2 weeks for the next talk. Have a good day, everyone.
Okay, hope to see many of you back.